We are going to start the mathematics literature for CMSA and Tsinghua series. We had this series start about 5 years ago. It was very successful since then. We are focusing on inviting distinguished people who lectures on the subject that of current interest and has important past history. And I was proud to start it at that time, but I feel that Dan, who succeeded me as a director of CMSA, has done better job, and I'm very pleased to see that CMSA is doing very well. All the speakers are excellent, chosen by committee, composed of people from CMSA and a group of people in Tsinghua University. We're very proud in Tsinghua to have cooperation with CMSA. So the lecturer has been very clear about what they say, and I learned a great deal for all these lectures. So I'm very proud to see Bjorn Poonen, who has been a good friend for a long time, from MIT, is going to talk. He was in Berkeley and in many important places, one of the most distinguished mathematicians and a great lecturer. So Bjorn is going to talk on the title of the rank of an elliptic curve. So we will learn from him. So Bjorn, let's start.
Okay, thank you very much for inviting me. So it's a real honor to speak here at the CMSA in this, especially in this series. So thank you, Professor Yao. Okay, so I'm going to talk about ranks of elliptic curves. But okay, so let me first. Okay. So let me just first talk about some easier curves. So we're going to be talking about plane curves, and so defined by a polynomial in two variables, x and y, and you can classify them by the total degree of the polynomial. So I mean, I think you all know that the degree 1 curves are lines, degree 2 curves are conic sections, just called conics, and degree 3 are cubic curves, and elliptic curves are special cubic curves. And so I'll say exactly what they are later. All right, so first so we want to study the so before I talk about elliptic curves, I want to talk about rational points on a degree 2 curve. And well, my favorite degree 2 curve is the circle, x squared plus y squared equals 1. And the problem is we want to understand the rational solutions, the rational points on the curve, the points that where both coordinates are rational. I mean, I skipped degree 1 because I think you all know how to find the rational solutions to the rational points on the line. So okay, so for this circle, you can start by observing -1, 0 is on the curve, and then you can get other points by drawing a line with rational slope through -1, 0, and looking at the second point of intersection. And that second point of intersection will always be another rational point, because if you imagined solving the system of equations, of the circle equation and the line equation, you'd end up having to solve a quadratic equation for which you already know that one of the roots is rational. And so the other one will automatically be rational. And so, and then by varying the slope of the line, you can get rational points. And conversely, every rational point on the circle arises this way, because you can always, given a rational point on the circle, you can draw the line through it and -1, 0. And so in this way, as t sweeps through the rational numbers, you parameterize all the rational points on the circle. Well, except for -1, 0. And if you work out the equation of the blue point as a function of t, then you get this formula on the right-hand side. Okay, so that's a complete description of all the rational points on the circle, and this is essentially the parameterization of Pythagorean triples that was known a very long time ago. So, all right, so yeah, and the same method works on any degree 2. On any smooth degree 2 plane curve, so which I'm also calling a conic. So if you want to describe this set of rational points, well, there's one issue that's maybe different from what happens with the circle, and there's one. It could be that your conic has no rational points at all, because on the previous slide, I needed that one rational point to get started, but fortunately, there's a way to test in advance whether there is a rational point. And it just amounts to checking some congruences. It turns out the only way that a conic can fail to have a rational point is if there's some kind of congruence obstruction. And so, I mean, in modern terms, you would say that this is a consequence of a much more general local global principle for quadratic forms in any number of variables called the Hasse-Minkowski theorem. And that says that that this curve has a rational point if and only if it has a real point and a p-adic point for every prime p. And in fact, you don't really need to check every, I mean, that looks, so I mean, this might look like a bad test because you're just trying to check whether there's a point over this one field Q, and now you have to check all these infinitely many fields. But in fact, the existence of p-adic points for almost all p is automatic. So it's really just finitely many fields you have to check, and it's very easy to check whether there's a real point, and it's almost as easy to check whether there's a p-adic point for any given p. So this is actually an actual test you can do, and in practice it's even easier for these conics because you can just, in fact, Legendre worked it out. You can just write these conditions in terms of the existence of solutions to some congruences. And just as one example, if you take the conic slightly larger circle, x squared plus y squared equals 3, then you can prove that that has no rational solutions, and in fact it has no solutions over the it has no three-adic solutions. And concretely, the reason that there are no solutions is because, I mean, if there were a solution in rational numbers, you would then have a solution in integers to this equation, and a solution in co-prime integers. But you can check that there are no co-prime integers x, y, and z that satisfy the equation mod 9. You can just check all the possibilities mod 9, for example, or something. Or it's, yeah. Anyway, so yeah, so that's an example. So okay, so this algorithm is 2 steps. So first you check whether there's a rational point. I mean, if there are no rational points, then you're done. You know what the rational points are. And if there is a rational point, then you can do what I was doing on the previous slide. You can just start with that one point and draw lines through it of rational slope and to parameterize all the other ones. And so yeah, and that gives you a so you in that case you can parameterize the rational points. I mean, in modern terms, the fact that this works is the fact that in algebraic geometry terms, any conic is isomorphic. Any conic with a rational point, any smooth conic with a rational point is isomorphic to the projective line over Q. Yeah, so I guess I'm switching here between talking about the affine curve defined by the inhomogeneous polynomial and its projective closure, where I homogenize the polynomial to get a quadratic form in 3 variables, and then look at the projective curve. Okay, so that's what I want to say about a degree 2 curves. And so the first really, so this is, well, I don't know if you consider this interesting, but maybe it was interesting like 250 years ago or two, but it's all known now. So let's move on to the case of interest, which are degree 3 curves. So, and again, I'm going to assume that they're smooth, so non-singular. And as happened for degree 2 curves, it's a smooth degree 3 curve doesn't necessarily have to have any rational point at all. But actually in this case, and unfortunately there's also no local global principle that holds in general for these. So it's actually not so easy to decide whether there is a rational point. But for now, let's just assume that there is a rational point on the degree 3 curve. And if you have a degree 3 curve, a smooth degree curve with a rational point, then you can do a change of coordinate to put the equation of the curve in some reasonably canonical form. And it's actually a little bit more than a linear change of coordinate, but it's a birational change of coordinate where the new coordinates are expressed as rational functions of the old coordinates, and vice versa. The old coordinates can be recovered as rational functions of new coordinates. So from the point of view of understanding the rational points, there's no harm in doing this kind of change of coordinate. And after doing that change of coordinate, then you have a curve that in this simple form, where the cubic curve is of y squared equals xu plus ax plus b, where a and b are some numbers. And well, this is the affine equation, and strictly speaking, the elliptic curve is the projective closure of this curve. So it includes, so if you want to describe it completely, you would homogenize this equation by putting in a z here, a z squared here, and a z cubed here, and look at the curve that this cuts out inside the projective space with homogeneous coordinates x, y, and z, and then that would be the actual elliptic curve. In fact, when you do that, you don't get much more. You just get the affine curve with one extra point at infinity. It turns out. Actually, yeah. So okay, so that's what an elliptic curve is. And okay, there is the condition that it should be smooth, and that you can express in terms of some discriminant being non-zero. And it amounts to saying that this cubic polynomial has distinct roots, no repeated roots, and so that means that this discriminant polynomial has to be non-zero. Okay, so yeah, so okay, so we're studying these because these are the simplest varieties whose rational points are not fully understood, because the next case beyond conics, and also they're interesting because they're the first examples of projective algebraic groups of positive dimension. So yeah, so the set of points on the curve has a group structure, and also the set of, and if you look at the rational points, the set of rational points has a group structure, and the group structure is defined by some geometric process, which maybe you've probably seen before. I'm not gonna. You draw a line through 2 points, and blah 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 blah, and then you get, yeah. Okay, so the set of rational points now has the structure of an abelian group, and Mordell over 100 years ago proved that this abelian group is finitely generated. So, and by the structure theorem for finitely generated abelian groups, that means that it's isomorphic to a power of z direct sum with some finite abelian group, and yeah, T. Okay, so it's, yeah, and an example of this is if you take Fermat's last theorem for the case of exponent 3. So then that's this curve x cubed plus y cubed equals z cubed in P2, and using a birational change of a coordinate, you can find that this is isomorphic to the projective closure of this affine curve y squared, which is in the form that I showed you on the previous slide, with capital A equals 0 and capital B equals minus 432. And then it turns out for this one, well, if Euler figured out what all the solutions to this equation are in rational numbers, or equivalently in integers up to scaling, and they're the only ones. I mean, you know, Fermat's last theorem is true, so it's true for this exponent too. And so the only solutions to this are the ones where one of the coordinates is 0. And so there are 3 such points in projective space satisfying this equation, and so you get the set of rational points has 3 elements, and I guess if you know it's a group with 3 elements, you know what the group is. So yeah, so it's this. And so yeah, so in this case, the rank is 0, and the torsion subgroup, which is this T, is this Z mod 3Z. Okay, so now the questions are, okay, can you understand how this rank and how the torsion subgroup behave for elliptic curves? So what are the possibilities? And for the torsion subgroup, it's a famous theorem of Barry-Mazur from 1977 that there are only a handful of possibilities for the torsion subgroup. There are only, I guess, 15 possible groups that it could be, and so it's either a cyclic group of order less than 12, and not cyclic of order 11, or else it's one of these groups. Okay, so that's in practice it's quite easy given the equation of elliptic curve to find the torsion subgroup. So the understanding of the torsion subgroup is essentially completely understood, and so the mystery, what remains as the mystery is the rank, trying to understand what the possibilities for the rank are, and even whether you can find the rank given the equation of the elliptic curve. And so this question was raised, in fact, even before it was known that the group was finally generated. I mean, I guess Poincare, he probably had some idea that it probably was finally generated, or he asked in 1901 what you could say about the number of generators you need for this group. And so you can interpret that as saying he's asking what the it's essentially the same question as asking what are the possibilities for the rank of the curve. All right, so let me just to show you. So this is I don't know if you can see this, people on Zoom, but it's a big table of numbers. This is not one big number. It's supposed to be a table. It's a table of one-digit numbers, and the meaning of this table. Well, you can see where the axes are. This is the capital A, capital B plane, and for each pair of integers A and B, I've plotted at that point the rank of y squared equals x cubed plus ax plus b. And well, you might notice that there's some places where there's no number, there's just a star, and those are the places where the discriminant is 0. For example, if A and B are both 0, then you get the curve y squared equals x cubed, which is singular. So that's not an elliptic curve. But for all the other ones, for most of them, there's an actual elliptic curve, and yeah, and the rank is, well, I mean, that's what it is. So, and the question is, do you see the pattern? Can you see can you predict? Like, can you guess what the next number on the right here is? I can't see, because you can't see my hand, but anyway, so yeah, can you predict based on this? Can you, what the, and you might know, I don't know, can you see any patterns at all? I mean, I guess you might notice, for example, that if you look at the horizontal axis and you go one row up, so then you might notice that the numbers in that row seem to be a little bit bigger than most of the other ones. And there's a good reason for that. Those are the curves of the form y squared equals x cubed plus ax plus 1. And those curves, they have a rational point on them. Namely, you can take x equals 0 and y equal 1. So you get one rational point for free. And most of the time, that rational point will be of infinite order. And so that already contributes 1 to the rank most of the time. And so you get sort of a +1 to the rank. And so it sort of, you might expect that it sort of shifts the distribution of possible ranks by +1. And that seems to be maybe what's happening there. Yeah, but I mean, but as you can see, it's kind of hard to, it's not so easy to see other patterns in this table. And well, based on this data, you might conjecture maybe the rank is never more than 3. Or yeah, and you might ask questions like, how often, what's the density of zeros? Like, what percentage of these numbers, if I made the size of the table bigger and bigger, what would be the asymptotic density of this number of the elliptic curves that have rank 0? And yeah, so you might conjecture that the rank is at most 3. You might conjecture that there's a positive fraction of elliptic curves of rank 2, and I don't know, there are all kinds of conjectures you might make, and most of these are actually believed to be wrong. It's believed that okay, well, maybe I'll say more about this later, but the actual conjectures that people make are that if you do let the box, this is just not a big enough table. So if you made it much bigger, you would see that about 50% of them were zeros and 50% were ones. And then all the higher numbers would be asymptotically 0%. And moreover, there are some elliptic curves that have rank greater than 3. There are, in fact, okay, so I'll say more about this in a second. All right, so any questions about this? Anybody want to point out some patterns? I don't know if people on Zoom can even talk to me, but anyway, it's okay. I guess you can type in chat or something. All right, so there's some algorithmic questions here. So first of all, can you actually compute that table? Well, obviously it's been computed, but in general, if I give you a smooth cubic curve, well, okay, there are 2 questions. One is just whether you can do the analog of what Legendre did for conics. Can you decide, given a smooth cubic curve, whether it has a rational point or not? And it's not known, yeah. how to do that. And it's not an easy question. You can't just, it's not enough just to check whether it has a real point and a p-adic point for every p. Because even if there are examples where the curve does have a real point and a p-adic point for every p, but still there's no rational point. So, and there's actually a group that measures this failure of this local global principle that's called the Shafarevich-Tate group, or possibly the Tate-Shafarevich group. It depends. The ordering of the names depends on whether you write the names in English or in using the Cyrillic alphabet. So I guess, so anyway, so yeah, so, and this group is, yeah, this is measuring the failure of the local global principle, and it's sort of analogous. There's a reasonably close analogy between it and the class group of a number field. The class group of a number field is the group that measures it measures the obstruction to for fractional ideals to be principal, to be generated by one element. Okay, so all right, so that's the first question, and and then there's another question, which is given an elliptic curve where you already know there's a rational point, can you compute the rank? In other words, can you compute the numbers in this giant table? And so I did it, or other people did it, or actually Magma did it last night. You can compute the numbers for these elliptic curves, but actually so there is a method that seems to work most of the time, but it's not known whether this method always works. In fact, the method that's used requires knowing something about the Shafarevich-Tate group in order to succeed. And in practice, it seems to succeed. So we are able to compute these tables, but we don't know whether we'll be able to compute it all the way out to infinity. So one interesting thing is maybe that these questions, they might look quite different, but in fact, if you have an algorithm for one of them, you get an algorithm for the other one. And this goes through the theory of Selmer groups, which I'll talk about a little later. So for neither question is it known whether there is an algorithm, but the answers to the two questions are the same. So, okay, all right. So there's some conjectures that would imply that you can solve these problems. So one of the conjectures is that this obstruction group, this Shafarevich-Tate group, is always finite for every elliptic curve. And okay, and then the other conjecture is one of the Clay Millennium problems, which is the Bircham-Swearingen-Dyer conjecture. And for this one, I have to introduce a little bit of notation. So okay, so if I start with an elliptic curve over Q, yeah.
There is a question.
Oh yeah.
Can we use AI to find some patterns in the numbers?
Okay, so you want to go, okay, let's you want to apply AI to this. So there are people who are applying AI to study these patterns and try to predict things like the rank. And I guess, yeah, sometimes on some problems I mean, it's hard, but they have discovered some new, using machine learning, they have discovered some new phenomena that had not been observed before. There's these things called murmurations, where it's some sort of, okay, anyway, maybe I mean, that would be a separate talk, and a talk for which I'm not the most qualified person to give. I'm not the most qualified person to give that talk, but yeah, but there has been some, I'd say, some limited success. Maybe not in predicting the rank of elliptic curves, but in observing some new patterns that hadn't been noticed before. So yeah. Okay, so I want to say at least what the Bircham-Swearingen-Dyer conjecture is about. So you start with an elliptic curve over Q, and so it's given by some equation, y² equals x cubed plus x plus b, and you can assume that the a and b are integers by doing a change of variable, and then you can reduce the equation modulo p, which means just to reduce all the coefficients modulo a prime p, and then you can count the solutions, the number of solutions to that equation over the field where the x and y now range over the finite field fp, or z mod pz. including the point infinity. And then if you take the number of solutions and you adjust it by, compare it to what the expected number of points you would have on a projective curve, and you measure sort of the deviation, then it turns out that this number that this deviation is bounded for almost all p. This deviation is bounded by 2 times the square root of p, and if you put these numbers, these deviations into and make some kind of generating function out of them, in the same way that you sort of analogous to the infinite product that defines the Riemann zeta function, then you get a function that, although it a priori converges for complex numbers of real part greater than a half, but that function turns out, well, this is using a lot of math, but it turns out it's known now that this function has an analytic continuation to the entire complex plane, so as to get an entire function of the complex number S. Okay, and that's called the L function of the elliptic curve. And the Bjorn-Dyer conjecture conjectures that the order of vanishing of this function at the point S equals 1, where this product doesn't converge, is equal to the rank of the elliptic curve. By the way, I cheated a little bit. You might notice that this is not an equal sign. That you do something a little bit different at primes where the discriminant reduces to 0. So anyway, it's essentially this. Okay, so yeah, so for example, if you knew that this conjecture were true, or if you knew that this conjecture were true, either one would let you solve the 2 algorithmic problems that I had on a previous slide. For example, for this one, if you know that this is always true, and somebody gives you an elliptic curve and you want to find its rank, here's what you can do. So by day, you can search for rational points in the elliptic curve, and given any collection of rational points, it's not too hard to find the rank of the group that they generate. And so in that way, you get lower bounds on the rank, because it just might be that you haven't found enough, you haven't searched far enough to get enough rational points to be generators yet. So that gives you a sequence of lower bounds, and we know that E of Q is finally generated. So it's a sequence of lower bounds that eventually will be sharp. But we don't know a priori when it's going to attain the actual rank. And then on the other hand, by night you can compute this function numerically, and you can compute its higher derivatives numerically, and you can try to, and for example, if you suspect that the rank is 4, what you can do is you can try to compute the 4th derivative of this function at 1. And if that 4th derivative, if you can compute it finely enough, if you can compute accurately enough to know that the 4th derivative of this function at 1 is not 0, that tells you that the order of vanishing of the function is at most 4. Or less, yeah, less, okay, anyway, less, I guess less, yeah. So that means, yeah, it's at most 4. And so that gives you a way to compute upper bounds by doing and then if the Bjorn-Dyer conjecture is true, then these upper and lower bounds will converge on the correct number eventually, and so then you will know the rank. So okay, so yeah, unfortunately, yeah. So and not only that, if you prove this conjecture, you get $1 million. So so yeah, okay.
Another question: is it known or believed that the rank can be arbitrarily large?
Yeah, that's sort of what the rest of my talk is going to be about. So you just hold on to that question. You might think from if I go back to this, it sure doesn't look like it from this. But yeah, but anyway, okay. So yeah, so these numbers do not seem to be getting very big. But yeah, but that's a very, yeah, it's definitely an interesting question. Maybe one last thing I'll say about the Bjorn-Dyer conjecture. There's some cases of it where it's known, and likewise there's some cases of this that are known. Yeah, for example, they're from the work of Gross and Zagier and Kolyvagin in the 1980s. Well, okay, strictly speaking, you also need the proof of the modularity of elliptic curves, which was done in the 90s and so on. But once you put all that together, then you know that these conjectures hold. And also in the Bjorn-Dyer conjecture, there are refinements of this that tell you not only the order of vanishing, but also that tell you the leading term in the Taylor series at 1 for this in terms of other arithmetic invariants of E. Okay, anyway, so they're known in this case where the order, where this order vanishing is least, is the most one, then it's true. So there's some evidence for it, but okay. All right, so now let me get to the question about, that I was just asked about, is it believed that the rank is uniformly bounded as you vary the elliptic curve? And so here's a table of the rank. So of the largest rank that's known, that has been known in as a function of time. So yeah, so okay, so already, so well, you can see it's, well, okay, of course it's increasing. So but the question, so and Néron in the 1950s, he found a general method, sort of a theoretical method of constructing elliptic curves of high rank, but without actually writing down the explicit equations. I mean, a simplified version of the idea is you choose a bunch of points in P2, and then you just use linear algebra to find a cubic curve that passes through all those points. And so in that way, you can get a smooth cubic curve that already has some number of points. So something on the order of 9 or 10 or something like that. And so, and then those points, most of the time, he proved that most of the time, those points will already generate a group of large rank. And using this plus some extra tricks, he was able to get elliptic curves of rank up to 11, at least. And then once computers became more powerful, and Mestre came up also some theoretical ideas for finding these high rank curves came into being, then Mestre was able to find even higher elliptic curves of even higher rank. And yeah, I mean, this should seem very surprising to you if you go back to that table I showed, because where all the numbers are like these three. I mean, you might wonder, like, how far out do you have to go? How big does that table have to be before you start seeing a number like 12? And yeah, it is pretty far out, but yeah. And then as the 80s and 90s went, people just kept finding, I mean, both algorithmic improvements and also just faster computers. They're finding better and better elliptic curves of higher and higher rank. And this continued for a while, and then sort of got stuck here for a while. But then Elkies found a rank 28 curve using some ideas using K3 surfaces and using the same family there, but using using some more improvements and a faster computer. And the Elkies and Klagsbrunn were able to find a rank 29 curve. So and that so far is the record. So I don't know. So I mean, you might look at this and say, okay, maybe we just have to wait for computers to get faster, and we'll, next year we'll find a rank 30 curve, and year after that it'll just keep going. Yeah. On the other hand, yeah, there are clues in, at least in the way that these elliptic curves are constructed, it does seem as if it's kind of petering out, that maybe at least the methods that are used, it seems maybe it's the case that they're not going to go on, that they're not going to find that this is not going to go on forever. And so, people have tried to answer this question. This is one approach to trying to understand the question of whether the rank is uniformly bounded. You actually try to search for the elliptic curves and see how high you can get. But you can also try to give some heuristic arguments to try to guess the answer. Like if you can predict, like if you're going back to this table, if you can find some sort of probabilistic model for how. Like if you imagine some probabilistic process that would generate a table of numbers that would look like this table, then maybe you can get some kind of idea of what the rank, how the rank should behave. And so this is an approach that has been very useful for understanding things about prime numbers. So there's something called the Cramer model, where you list all the positive integers starting from 2, and then, or maybe starting from 3, and then you choose each integer or not. You choose each integer with probability. You choose n with probably 1 over log n, and because that, and then you get some sort of random sequence of positive integers, and the choice 1 over log n, that's supposed to be approximating the probability that a number of size around n is prime. And so when you do this, you get some sequence of numbers that kind of looks a little bit like, it looks, at least superficially, it looks like the sequence of prime numbers. And then you can ask if you want to know the answer to questions about prime numbers, like is every even integer at least 4 the sum of 2 primes? You can try to guess what the answer is by seeing whether it's true in this Cramère model, if it's true probabilistically with high probability. And so you can at least guess what statements about prime numbers might be true that way. And so we'd like to do something similar here. Yeah.
There are a couple more questions. One about this table. There are several rows with zeros, or with few zeros, actually. Do we have an algebraic explanation for that?
So for some of them, some of the ones, like the row just above the red one, it's there because, as I was mentioning, there's a causal rational point there that most of the time has infinite rank. So it sort of gives you a rank 1 at least already. I think there are some. Yeah. So I guess for the other ones. Yeah, and so for any at 1 and for any, I think, yeah. So any row with where the b coordinate is a square of an integer, you should get that elevated rank. And down here, I guess there are no such rows, but it's not really known what the distribution is. I think maybe it's reasonable to guess that in any given row, that maybe the conjecture still should be that 50% are 0 and 50% 1, and everything else is asymptotically negligible. That might be a reasonable thing to guess, but I think there's not really any theorem, I think, about that, unless I'm not sure if it's just yeah.
And another question: is there a formula that bounds the rank in terms of A and B?
Okay, so the question is there a formula that bounds the rank in terms of A and B? So that there is a function that you can give, and this is based on the theory of Selmer groups, that you can give some function, but that function goes to infinity as A and B goes to infinity, so it's not clear whether that bound is even close to being sharp. But there is some bound that involves things like the number of primes dividing the discriminant and the size of certain class groups of number fields. But all these things are computable. So given A and B in practice, yeah, you can compute some upper bound for what the rank is. So, but determining the rank exactly, that's still not known. At least, it's not known whether it's not proved that you can do that always. Okay, are there more questions? Okay, good. So, all right. So let me go back here. So these are the records. Yeah. So okay. So here's the question you were asking: is the rank bounded as you vary E over all elliptic curves? And the general, the folklore conjecture about this has sort of flip-flopped a couple of times. So early on, people conjectured that there should be a uniform bound. So Néron, even though Néron was the first person to find these elliptic curves of rank 11, he actually himself thought that the rank should be bounded. And and then other maybe, and then I think then Castles wrote a survey article where he conjectured that the rank should not be uniformly bounded. And I think, well, I don't know, he's a person of authority. I think a lot, well, maybe I guess a lot of people followed him, and they also reported that it became sort of a folklore conjecture that the rank should be unbounded. On the other hand, more recently, there have been various authors who've given various heuristics to various models that suggest that maybe actually the rank is bounded. So I don't know, I think if you talk to experts in the field, I think you'll get a split opinion about whether it's bounded. But I want to convince you why I'm right, and so why it actually should be bounded. So this is going to be a probabilistic model that I'm going to present. That models not just ranks, but also predicts the behavior of other objects all at once in one big package. My ranks, Selmer groups, and Shafraevich-Tate groups, and simultaneously. And the advantage of having a heuristic that gives you for predicting all of them at once is that you can check. You're not just checking. You have some way to check like certain pieces of the prediction, because when you have this whole package of modeling this whole package, there's certain consequences of those predictions that are more than just about ranks, and you can check that at least those predictions are correct. And so that gives you some sense that you're on the right track. That if your model predicts some correct things, I mean, I know this is the wrong way. This is not the, yeah. Anyway, it's backwards logic. But anyway, it gives you some, at least it makes you feel as if you're doing the right thing. Okay, and the model that I'm going to present will actually predict that the rank is bounded by 21, with finally many exceptions. And it's good that it's good that our model allows for finally many exceptions, because we already know that there are some exceptions going up to rank 29. So, all right. Okay, so in order to explain this, I'm going to have to, okay, so I'll have to say some more things about elliptic curves, and in particular, I'm going to have to tell you about Selmer groups. So this is, okay, so first, let's try to, so what's going to be, one thing that's going to be important is to understand how many elliptic curves there are where the A and B are up to a certain size. And so this is not too hard to figure out. So first of all, you can, if you want to, some of these elliptic curves you get when you take integers A and B, some of them will be isomorphic to each other. Sometimes, for example, if you multiply A by a 4th power, and you multiply B by the 6th power of that same number, then there's an easy change of variable where you can scale the x and y to show that the two curves are isomorphic to each other. And then the ranks will be the same. And so usually you'll look at these elliptic curves up to isomorphism. And one way to fix a representative of each isomorphism class is to assume that you cannot do any more. You've already undone any of these possible scalings. So there's no prime whose 4th power divides A and simultaneously has 6th power dividing B. So it's like putting the curve in some kind of minimal form. And okay, so we'll look at those. And so we'll call this curly E the set of all such curves. And so that's some countable set of curves. And yeah, when we say things like something holds for all but finally many elliptic curves, that means all but finally many isomorphism classes, or all but finally many E in this set. And we're going to want to measure things like, ask questions like, what is the average rank? And to talk about averages, we'll want to, if you're averaging a function on a countable set, you have to, what you have to do is you have to take a large chunk of that finite set and average over that finite initial segment of the, so you order all the elliptic curves by using some height function, and then you average over the elliptic curves of height up to a constant h, and then you let h go into infinity. And so, okay, so the height is going to be defined. This is just some measure of the size of A and B. And well, for various technical reasons, it's convenient to use these numbers. These are the two monomials that appear in the discriminant. And but height is basically controlling how big A and B are. And then I'll just use, just for simplified notation, we'll let this be the set of elliptic curves of height bound by this. So this is going to be a finite subset of this countable set for any given number h. And it's easy to figure out how quickly this finite set grows Because if you're asking for an elliptic curve to be of height at most h, that means that A can be only up to about h to the 1/3, and B can be only up to about h to 1/2. So ignoring constants. And so the number of pairs of A comma B you have will be about h to the 5/6. And you can show that's still true even once you impose conditions like this. This only changes the constant. So okay, so they're about h to the 5/6 elliptic curves of height up to h. Okay, so the other thing, now this is going to take a little while, but I'm gonna need to define what a Selmer group is, because the Selmer groups are well, let me first tell you why we're going to define these groups. So the Selmer group, there's only one way known to get upper bounds on the rank of elliptic curve. The only way known is to bound the rank in terms of the Selmer group that I'm going to define. That's the only way to get provable upper bounds for the rank. And so the Selmer groups are going to be some computable group, something that you can compute given the equation of the curve, and that will give you it'll give you some finite upper bound for the rank. All right, so you start. Okay, so the starting point is you write down this exact sequence. So Q bar here denotes an algebraic closure of Q, and E of Q bar denotes the set of points satisfying the equation of E, where the x and y coordinates lie in this field, Q bar. And by algebraic geometry, you can show that this group is a divisible group. So if you have any point on the elliptic curve P, there will be some other point Q such that 2Q, for example, 2Q is equal to P. So you can always divide by 2. Except when you're dividing by 2 to find the coordinates of Q of the half, the coordinates will satisfy to say that the coordinates of that point that doubles to give you the specific P. It amounts to some algebraic equations that you have to solve in order to find the coordinates of that half point. And there's no reason that those algebraic equations, I mean, they're not linear equations, they're higher degree. So you might need to take square roots or things to find the solutions to those coordinates of that half point. And so typically, even if you take a rational point, which is meaning you're taking a point here that's Galois invariant, there's no reason that it should be, I mean, it will be double something, but it might not be double of a rational point. So we'd like to measure the obstruction to writing it as twice a rational point. And that's what Galois cohomology is good for. So it tells you that if you take the Galois invariance of the sequence, then it's no longer exact, but there's a group here that measures the obstruction to dividing by 2 inside E of Q. And that's this group. That's this first cohomology group of the Galois group of Q acting on this finite group. This turns out to be a finite group as a group. It's Z mod 2Z cross Z mod 2Z, but there's a Galois action on it. And the idea is if you have a rational point here, you can take some half of it, but then because that half of it won't have rational coordinates anymore, you can act on the coordinates by the Galois group, and it'll get moved around, and you can measure how much it moves around, and that's what the cohomology class here is measuring. It's measuring the failure of this half point to be rational. And so anyway, so you take the Galois invariance of this. So you get E of Q mapping to E of Q via the 2 multiplication by 2 map, and then it goes on to this group. And then you can, in fact, you get a whole long exact sequence, but you can contract it by replacing the group at this point by the co-kernel of this one, and that'll be this group. So this is the group that's measuring the failure of this is the group that really is the obstruction to taking a rational point and dividing it by 2. So it's telling you and then but you can measure that obstruction as by this cohomology by an element of this cohomology group here. And so and this is good because if you were able to compute this group, this would tell you the rank, because I mean in fact this group is almost, I mean the size of this group is almost Z mod 2Z to the rank. I mean there could be a little bit of contribution from the torsion subgroup as well, but but we can easily compute the torsion subgroup, and you can subtract that out. So if you know this group, you'll know the rank of E of Q. And so the idea is to find what this group is, try to figure out what its image in here is. And the advantage is that on this side, you don't have any algebraic geometry anymore. You just have this finite group of 2 torsion points, which is of order 4. And then the only complicated thing is you have a big Galois group acting on it, and you have to take cohomology. So yeah, and so okay. So the idea is in order to understand this group, try to figure out what its image is in here. And this okay. Now, and I mean, this is supposed to be a finite group, and we want to bound its size. But unfortunately, this group is always infinite. It's some infinite dimensional F2 vector space. And so it's too hard to figure out directly what this image is. And so what we'll do is try to work with locally to try to get constraints on what the image could be. So to get a better upper bound inside this infinite group where this finite group lands. And so to do this, you can do the same construction that gave this, but over a local field, over the field of p-adic numbers, and you'll get a similar. There'll be a similar exact sequence here, and you can take Galois cohomology, and you'll get a homomorphism here, and this sequence also maps to this sequence just by, well, over here a rational point, you can just reconsider it as a p-adic point, and then in here there's some restriction map of Galois cohomology, just because the absolute Galois group of QP it can be embedded as a subgroup of the absolute value group of Q, by just restricting an automorphism of QP bar to an automorphism of Q bar. Okay, and the nice thing about this is that this map is a lot easier to understand because these are, just because arithmetic over p-adic numbers is easier than doing things over the rational numbers. In the same way that solving equations over the real numbers is easier than trying to find solutions over the rational numbers. So okay, so once you have this diagram, you see that this gives you a constraint on what the image of this global map could be. Because if you have some point here that is in the global image here, then when you map it down here, it must be in the image of this local map, because whatever it came from, you could map it this way as well. So this image must map, the image of the global map maps to the image of the local map. And so this cuts out a subset of this big cohomology group, a subgroup in which the image of the global map must lie. And you can do this not just for one prime P, but you can impose this constraint. You can cut this down by these subgroups for all the primes P. So and you can also do this for the real numbers, which instead of the p-adic numbers. So I'll just write that as Q sub infinity. Q sub infinity will just mean the real numbers. And so in this way, by putting these products here, I'm imposing these local conditions on elements here for all primes P. And so yeah, and so that it turns out that those cut down this group, this infinite dimensional vector space to a finite dimensional vector space. And that's what the Selmer group is. So the Selmer group, the 2 Selmer group of E, is the set of points, is a set of elements here, such that it's a set of elements C in here, such that when you map it down, it lands in the image of all the local maps. So it's locally in the image. And so that's an upper bound then. That's a subgroup of here, that's a group here into which this group must land. And so, yeah, and it turns out that this group, this 2 Selmer group, using some classical theorems of number theory, you can prove that this Selmer group is finite and also computable. And so it's a good proxy for, it's a good for this group that we would like to know. So, but unfortunately, it only gives you an upper bound. So it doesn't tell you the rank exactly, but if you know the 2 Selmer group, that immediately gives you an upper bound for the rank. And so that's what it's used for. And so what you would like to know then is how good an upper bound is it? Is it close? Is it close to measuring the actual rank of the elliptic curve?
Someone asks if the diagram commutes.
Oh, yes, the diagram does commute, yes. It's important that it's a good question. It's important that it commutes because it's the fact that this commutes. That's what tells me that the image of the global map maps under beta to the image of the local map. So that's what tells me that the image of the global map will be contained in this Selmer group. Okay. Any other questions? No. Okay. So we'd like to measure how good an upper bound this is for this quotient. And there's an exact sequence that measures the difference. In fact, and you can do this not just for the 2 Selmer group, but you can analogously define the n Selmer group for any n at least 2. And then the difference between this upper bound and the group that we'd like to compute is measured by the n torsion in this mysterious Shafrevich-Tate group, which, yeah, and so this, well, okay, so that's what it is. So it would be really nice if this group weren't there. So if that group weren't there, then the Selmer group would be telling you everything about the rank. But, well, it is there, and sometimes it's not trivial. So, and sometimes it's helpful when you're doing this I mean, you can do this. You can compute the 2 Selmer group. And it turns out if you compute the 2 Selmer group, it gives you some bound of the rank. If you then compute the 4 Selmer group, the 4 Selmer group sometimes will give you a smaller upper bound on the rank. And then if that's not good enough, you can compute the 8 Selmer group, and so on. And so at least theoretically, you can take a colimit. You can take the colimit of this sequence as you let the n range through powers of a fixed prime, and then you'll get an exact sequence that looks like this. So this is just defined to be the colimit of these groups and then you'll get the union of all the p power torsion in here, and then over here you'll get something that, again, this group will if you can figure out what this is, how many copies of QP mod ZP there are in this, that'll tell you the rank. So if you can figure out this, then it'll give you the rank. And so we'd like to use this sequence and model this whole thing, have some probabilistic model that constructs a sequence of ZP modules that behaves the same way as the actual sequences that come from elliptic curves. And so that's going to be the strategy. Okay, so all right, so before telling you what the model is, and let me tell you first how you model an individual Selmer group. How do you predict? We know it's for example, if we take n to be a prime number, then this is supposed to be some fine dimensional FP vector space. And the question is, what's the how often is it 0-dimensional? How often is it 1-dimensional? How often is it 2-dimensional? And so we'd like to say what that is. And I mean, you can try to compute it numerically and see what happens, or you can, in some cases, you can actually prove theorems about it. And based on some of those results that were proved about it for the 2 Selmer group by Heath Brown in the 1990s, he proved that in a certain family of elliptic curves, you had a particular distribution. And so then you can ask, okay, what is a linear algebra construction? Forget elliptic curves. Is there a simple linear algebra probabilistic construction of a random F2 vector space that gives you that kind of distribution? And it turns out there was one. And so this led to a model that I and Eric Rains conjectured models the P Selmer group. And so maybe I can tell you what this is. So here's the linear algebra model. Okay, so forget elliptic curves for a second. We'll just start with a fine field FP. Take a 2n dimensional vector space over FP and equip it with this quadratic form. So my coordinates on this vector space are x1, y1 up to xn, yn. And I'll take this sort of standard hyperbolic quadratic form where I take the sum of x1, sum of xi, yi. And then, okay, so that's some function. And then if you have a subspace of this 2n dimensional vector space, it's called maximal isotropic if first of all, the quadratic form vanishes on that subspace. And also, if you take the bilinear form associated to this quadratic form, then Z should be self-dual with respect to that bilinear form. So, okay, so an example of this would be if you just took the subspace of this where all the y coordinates were 0. So that's an n-dimensional subspace of this. It's a half this dimension of the whole space. If all the y coordinates are 0, then the value of q everywhere on that subspace will be 0. And you can also check that that subspace is self-dual. Yeah, I mean, anytime you have a maximal isotropic subspace, then it's dimensionally half the dimension of the whole thing. And yeah, so it's certain subspaces of half dimension. And this is a finite field. This is a finite field. So there are only finitely many subspaces altogether for any given n, and for any given n p. So it makes sense to choose a maximal isotropic subgroup at random. And as I said, it always has half the dimension. But the interesting question is what happens when you choose two maximal isotropic subspaces and you intersect them. Because the intersection can have some variable dimension, some between 0 and n. And then if you look at how if you look at how that, and you think of that as a random variable, the dimension of that intersection, and then it'll have some distribution. And then, well, then you can also take that distribution and look what happens to it as the ambient space gets bigger and bigger as the little n goes to infinity. And it turns out that the distribution on that intersection dimension tends to some particular distribution on non-negative integers. And then we conjecture that distribution on that distribution on non-negative integers behaves the same way as the dimension of a random p Selmer group. And yeah, so that's the conjecture. And there are various reasons to believe this. And so first of all, well, it was partly inspired by what was proved in the p=2 case. That's in fact that's where this model. I mean, basically what we did to find this, we just thought to ourselves, okay, we know what this distribution for elliptic curves is supposed to, for Selmer groups, is supposed to look like for two Selmer groups, and we just said, okay, let's just think of all the ways we can generate a random F2 vector space, and see what the distribution are, and see if we can find one of these distributions that matches the predicted one that he's found, and we just kept trying things like, oh, first we tried, it's maybe symmetric bilinear forms and a co-kernel of a random matrix. And this was the one that actually matched the right distribution. So yeah, so anyway, but after the fact, we actually found that it's not just that the end distributions are matching. There's actually something in the arithmetic of elliptic curves. And after the fact, we found that the Selmer group really is an intersection of two maximal isotropic subgroups in something that you can define using the elliptic curve. So that's further evidence that the structure is actually there the structure is actually there in the arithmetic of elliptic curves. So it's it seems very reasonable to believe this. Now, and also once you have the average, once you know the distribution of the Selmer group, you can compute things like the average size of the Selmer group for a fixed n. And there are various people who've done that. So Johan de Jong in the function field case, and Manjul Bhargava and Arul Shankar in the number field case for n from 2 up to 5. So they determine, for example, they prove that the average size of the average number of elements of the two Selmer group, Bhargava and Shankar proved that the average size of the two Selmer group was 3. And so you can ask, so you can look at if you generate if you do this maximal isotropic subgroup spaces, you can actually compute what does this predict that the average should be, and well, we also get 3. So it does, and same, and you can do the same for 3, 4, and 5, and yeah, I mean, in general, the average size of the Selmer group it's predicted to be the sum of the divisors of n. So for this average size of the 4 Selmer group is Barger von Shankar proved that the average size of the 4 Selmer group is 7. And yeah. Okay. And there is also recent work by Tony Fung, Aaron Landsman, and Eric Rains, where they prove some kind of function field version of this statement. Maybe I won't try to explain that, but okay. Anyway, there's quite a bit of evidence in various directions for this conjecture. Okay, so but now going back to here, remember I was looking in order to get. I mean, the P Selmer group is good; it gives you some bound, but to really understand ranks, you need to look at not just. You expect to look not just at the P Selmer group, but also P squared Selmer group, P cubed Selmer group, because those higher Selmer groups will give you better upper bounds on the rank. And so we really wanted to, and we can take the limit to get even better. And so we really want to model this whole the P the infinity Selmer group as well, not just the P individual P Selmer group. And so Eric Rains and I joined with a bunch of other people, Mordell Bogova, Daniel Kane, and Hendrik Lenstra, and together we found some sort of linear algebra. We have some linear algebra probabilistic construction that we conjecture should model all these Selmer groups. So for the PVE Selmer group for every P, and even a distribution for the type of this whole sequence. And so yeah, so and again, it's compatible with everything that's known. So well, we believe it's true. Yeah, and so when you do this, when you get this distribution for this sequence, you get in particular you can also get a conjectural distribution for the P primary part, this P power torsion of the Tate-Trauff-Average group, as the elliptic curve varies. In fact, and you can also condition this distribution according to the rank of the elliptic curve. For example, you can ask, okay, suppose I look at I only look at elliptic curves of rank 2. What then is the distribution of this group? And it turns out that we conjecture it's a different distribution depending on what the rank is. And the way that the distribution depends in the model, at least, the way it depends on the rank is that it acts like this group. It acts like the torsion subgroup of the co-kernel of a random matrix, a random p-adic matrix that's alternating, so skew symmetric, and not just any random matrix, but to get the distribution for rank R elliptic curves, we think that what you're supposed to do is take a random matrix that's conditioned on the kernel of the rank being R. And so because of this result, we kind of believe that this rank of this kernel should somehow be what the rank of this kernel of a random matrix should be behaving like the rank of the elliptic curve. And so the next idea is to turn this around and say, well, suppose you didn't condition on this rank. So you just choose this random matrix you just choose this matrix at random, and you just look at what possible ranks of kernels come out. Maybe that should be the distribution of the rank. And if you do that, you find, if n is large and of random parity, what you find is that this rank, you do get a prediction for this rank, and the rank turns out to be 50% 0 and 50% 1 and 0% anything higher, which is nice because that's what other people had conjectured. So Goldfeld had conjectured in the 1970s. That should be what happens for elliptic curves. But if you want to know whether the rank is bounded, you need to look into that 0% that has rank at least 2. Because I mean, 0% means asymptotically 0%, but it doesn't tell you how high the rank. I mean, there could be very rare elliptic curves that have higher and higher rank. And so you need to make something a little more refined. And to do that, I mean, you can't do that by choosing random matrices over ZP, because I mean, the locus where this kernel will have higher rank will be some subvariety in the space of matrices, and it'll be a measure zero subset. It'll be like it'll be something, it'll be a lower dimensional variety. So the idea is, instead of looking at p-adic matrices, you can try to do this with integer matrices of a given size. And then if you take integer matrices of a given size, where the entries have a given size, then there's if you have a bounded size, you can ask there is actually some non-zero probability that a given integer matrix, the given lattice point will lie on a given, satisfy a given equation. So it's not just measure zero. And so, okay, so here, anyway, let me just tell you what the final model is for how to model the rank of the elliptic curve of a given height. So, okay, so there are going to be some functions, some growing functions, and in the first you choose a large integer n that grows. It's something large whose size depends on the height, and you choose it at random parity. You choose some random matrices with random integer matrices from the finite set of matrices whose entries are bounded by this other bound, and then and then you can define what should be modeling the Shaffer-Take group and the rank. So the rank, as I said, is the rank of the kernel, and then the co-kernel as a map from z to the n to z to the n. The torsion subgroup of that should be acting like this, and these are supposed to model these two groups. And yeah, so. And then to find out how quickly these group functions are growing, we chose this in order we wanted this to grow at this rate in order to match some theorems that were known about the distribution, the average size of the actual Shaffer-Take group for elliptic curves. So we sort of calibrate the model according to get that, and then and so that turns out that the right rate of growth of this function should be h to the 1/12. Okay, and so now you have now this is a very once you fix these functions, you have a very specific model. It has nothing to do with elliptic curves. It's just random matrices, but it's predicted that whatever this probabilistic construction outputs, whatever you get out of these random matrices, those should behave like the rank and Shaffer-Take group and rank of elliptic curve. And so now the point is, so this is like the analog of the Cramer model, where you're making some sort of, where in that model you're generating some random sequence of integers that's supposed to behave like the primes, even though it really has nothing to do with the primes. It just has the same similar density properties as the prime numbers. And this is this is an analogous thing, where we're looking at some collection of numbers that should be like the ranks of elliptic curves. And so inside the model, you can prove theorems about this probabilistic linear algebra. And so this is what I did with Jennifer Park, John Voigt, and Melanie Matchett-Wood. And so in the model, you have this things for each elliptic curve. There's this random variable that's just defined using linear algebra, the called pseudo rank, and you can ask what is the distribution of how often do you get rank? Does that pseudo rank equal something? And so altogether, if you look at all the elliptic curves, then the number of those up to height h is h to the 5/6. So I explained that earlier. H to the 5/6 is the same as h to the 20/24. And then if you do if you study the probability and you figure out what's the probability of having the rank of this kernel of this random matrix be at least 2, you find that it's less, that the probability that it's ranked at least 2, it turns out to be h to the -1/24. And so of the h to the 20/24 elliptic curves, only h to the 19/24 of them are expected to have rank 2, if you believe that this model is actually, so and for the pseudo ranks, that's a theorem that's how many elliptic curves of pseudo rank at least 2 there are. And and each time you ask for one higher pseudo rank, we prove that the probability goes down by another factor of h to the 1/24. And so, well, eventually you can see where this is going. Eventually, once you get up to 21, then this exponent becomes 0. I mean, we don't know whether it's actually positive or negative because, I mean, our model's not fine enough to figure out which direction this little o of 1 is going. But if you go one step further, then it should be then the model predicts that there should only be finite because so they're just not the heights are growing too quickly for the elliptic curves and then as a function of the height it becomes extremely unlikely that these very large height elliptic curves will have high rank. And so yeah, so okay, so this is the theorem, and then the conjecture is that the actual ranks behave like these pseudo ranks. So that's the part that's of course not proven. That this random this is just a theorem of probabilistic linear algebra of random integer matrices, but we believe that it should have some connection with the reality of the arithmetic elliptic curves. Okay, and so now you can ask, okay, how does this actually reflect reality? I mean, this is just some probabilistic model. You can just what is known is it actually true that there are only finitely many elliptic curves of rank greater than 21? And we don't know, but so far the record for an infinite family is due to Elkies, that he proved that there are infinitely many elliptic curves of rank at least 19. So far it's close but it's not contradicting our model yet. So and okay, and as I mentioned before, the absolute record is that there's an elliptic curve of rank at least 29, but they only found one of those. And so that's also consistent with there being finitely many of rank at least rank greater than 21. So far the data, I mean, the actual ranks that we observe seem to be consistent with the model. We don't know if it'll stay that way, but anyway, we'll see. You can also, as a further corroboration of the model, you can try to adapt the model instead of looking at all the elliptic curves over Q, you can classify them according to the size of their torsion subgroup. So, for example, let's look at all the elliptic curves whose torsion subgroup is Z mod 9Z and ask what in that family what do you expect the maximal rank to be? And the thing about these is there are very few elliptic curves that have this torsion subgroup. So a certain equation has to be satisfied and so on. And so instead of having h to the 5/6 of such curves up to height h, you only have a much smaller number of elliptic curves, h to the 1/18. And so they're much sparser. It's a very sparse subset of the elliptic curves. And because of that, you have fewer chances to get high rank. I mean, because the probability of getting high rank decays very quickly as the height grows. And so if you trace through the probabilistic linear algebra, our rank bound predicts that among this family of elliptic curves, instead of 21, there should be only finitely many elliptic curves of rank greater than 2. And you can ask, okay, how does that conform to reality? And in that case, well, there is an infinite family of known where the rank is at least 1, but yeah, it's not beyond that. And in every case, you can see that. I mean, it looks good. So I mean, this is the bound that beyond which we expect to have only finitely many. Our model says there should be only finitely many beyond it. And in each case, this is the record for the highest rank example of an elliptic curve, of an infinite family of elliptic curves that has that torsion subgroup. And so far, I mean, there's some cases where it's close. And actually, okay, so I should say one thing. So you see, I don't know if you see these little stars here, but it's expected that in those families, actually, it doesn't. It's expected that in that infinite family of rank 3 things, it's expected for some parity reasons that half of them actually do have rank 4. So it's not. Our model doesn't seem to quite capture everything. It seems to be slightly off in those cases, but anyway, it does seem that there's something correct about what we're doing. These numbers it looks, it almost, I mean, the data almost looks like it's fabricated. It looks like it's too good to be, almost looks like it's too good to be a match. But the heuristics seem to do very well at predicting like what we should be seeing in terms of elliptic curves of given rank. Okay, so yeah, so just to summarize all this, yeah, I mean, I've gotten into quite a few technical details, but just to summarize, so we defined Selmer groups, and then the heuristics for those gave those linear algebra model that gave a linear algebra model, probabilistic linear algebra model for a complete package, giving that's capable of predicting not just the Selmer groups but also the ranks and Shaf-Average Tate groups. And a lot of the aspects of the model are, you can prove that what the predictions they give are actually they're theorems in the arithmetic of elliptic curve that say that the model is giving you the right answers for some of the questions. Some of the implications of the model are supported by theorems. And then in the model, at least, these pseudo ranks are bounded by 21 with finally many exceptions. And so based on that, we believe that the actual rank should be uniformly bounded. I mean, maybe the bound isn't actually 21, but it would be I would be surprised if it were like if there are infinitely many of rank more than 100. So I mean the model would have to be very wrong in order for elliptic curves to be unbounded. I mean it's still possible that could happen. Maybe there's some special algebraic subset for some algebraic reason. I mean, who knows? There could be some causal reason why there could be something that our model is not capturing, something in the arithmetic of elliptic curves. But so far there's not anything known in the arithmetic of elliptic curves, either conjecture or observed, that would go against our model, really. So, okay, so let's see. So I should end like how much time should I? 2 minutes? Okay, well maybe yeah. I'll just say. I mean, maybe I'll just say here that. So I've been talking the whole morning about elliptic curves over the field of rational numbers, but you can generalize. You can replace Q by other number fields like Q join I, or Q join the square root of 2, and look at elliptic curves with coefficients in that number field, and so for any you can replace Q by any finite extension of Q, and you can ask the same questions, and the similar heuristics apply, and with some, and you can also look at function field analogs. You can look at, instead of a Q, you can look at FP round bracket T, the field of rational functions over a finite field, and find extensions of that. And in those cases, there are the model doesn't fit perfectly, but it doesn't fit as well, the predictions, but you can get good predictions again. That at least it seems that there might be some boundedness statements if you exclude elliptic curves that have additional structure, like elliptic curves over Q join I that really came from an equation defined over Q. If you exclude those, then it seems to work. And there's also an argument, you can also try to generalize this to higher dimension, to projective group varieties in higher dimension, and those are called the Abelian varieties. And if you look at Abelian varieties of fixed dimension over a fixed number field, then you can similarly there are reasons to believe that also for those also the rank should be uniformly bounded. Okay, so I'll stop here. So thank you very much for all your attention. Yeah.